Good morning, everybody, or maybe other part of the day, wherever you are. My name is Haim Cohen. I work at Bloomberg LP as a software engineering team leader. I've been in Bloomberg for 18 years in various roles, so you can say I got to probably introduce a lot of legacy code, and I'm glad to say I deleted some of it. Before Bloomberg, I worked in Intel and analog devices. I have a bachelor degree in computer software engineering from the Technion, Israel Institute of Technology, and master's degree from Columbia in the state of New York. Lainey.
Hi, I'm Lainey Hall. I also work at Bloomberg on Haim's team, and I'm sort of heading up the initiative we're going to be talking about today. I've been at Bloomberg for about 4 years, and I have a bachelor's in mathematics and computer science from Boston University.
Cool. Before we start, I want to give a big thank you to the organizers of this conference. This is the second time I'm attending it. I think it's an awesome conference. There should be many more conferences about legacy code beside this. I'm happy to be here. Today, so let's start. Today we're going to talk about how a 40 years old software company like ours, Bloomberg, keeps its code fresh and maintainable. All right, so it is 1982, okay? Talk about a brief history of Bloomberg. It's 1982. Mike Bloomberg, here to the left, has been fired from a company that he worked for, Solomon Brothers. So he got fired, just didn't get along with some people there, has been pushed into like a niche side, which is technology back then. So the front and the center of the company is bonds trading, and he has been pushing the technology, eventually got fired. So he's starting a new company. Back then it wasn't called Bloomberg LP. And he started the company with 4 employees. 3 of them are here in the photo. No customers. He got some coffee and bagels. So you can see at the corner of the room at the back, there is a fridge. No clients. Everything there is pre-PC era. So they have to create their own hardware. As you can see here, one of the co-founders, Tom Secunda, has a printed circuit board to the hardware. Windows was not a thing. Eventually, Windows picked up, and with the internet, the company moved into that. So this is 1982, how Bloomberg started. 40 years later, so a lot of things happened since then. Fast forward, this was taken in 2022. I think kind of toward the end of the pandemic in our New York City headquarters in Lexington Avenue, we have 350,000 Bloomberg Professional Service subscribers, plus a lot of enterprise clients. We have about 2,700 journalists and analysts globally producing unique contents for our subscribers. Some of it is available on the Bloomberg app that you can download. We have over 7,000 software engineers out of about 20,000 employees. Last but not least, I want to mention something unique about Bloomberg these days. We have been working on purpose. So Mike and a lot of his founders did very well. It's not a secret that Mike is a wealthy person. However, Mike decided as a personal decision to give majority of the company profit to his funds called Bloomberg Philanthropies in his effort to do good things, basically save the world. So majority of the profit that comes out of Bloomberg LP are going to charity. You can look it up, bloomberg.org, and that's where we are. So the question is, 40 years of software. We have been creating software since 1982. You can imagine what kind of tech and what kind of language have been involved, but how do we actually keep our software fresh and easy to work with? So we have an insight. Successful code is messy. Okay, so there are kind of a cyclical dynamics here. The code is messy because it is a successful. Successful code tend to be messy, and why? when you start a company, when you develop a product, you have rapid growth. You have very quick iterations to discover what your clients needs. Your business requires all sorts of accommodation of new features. It is not yet clear for the software that you're creating if the software is still going to stay around. So are you going to write tests? Are you going to write it maintainable? Does it really worth the effort? You don't know. And you don't actually have the time, because in many of these cases, and that was the case at the early days of Bloomberg, if you didn't get a product out of time, there's not going to be revenue, and it will be very hard to pay people to stay around. Okay, so that's the cycle of that's the era of success leading to code being a bit messy. There's the other way around, that the messy code is leading to the code being successful. So the code sometimes appears messy, and something we call the code messy, because the real world is messy. In our world of market data and user analytics, think about what we're dealing with. We're dealing with different countries, different rules, different regulations. Rules are created and uncreated. Countries and collection of countries like the European Union and EU, all of these things are created and uncreated. New countries, cities moving between countries. So not every business problem that we have can perfectly and generically be modeled, nor that it should be. So that leads to what we call what appears to be a messy code. However, the code needs to be able to respond well to changes. And I believe that when the code works well and we're able to evolve it, the beauty of the code is in that functionality and the ability to evolve it. And yes, sometimes it may appear to be messy. So the key takeaway here is we need to maintain our ability to evolve the code. So I'm going to start with a story. Didn't happen to anyone, right? You're on call, right? You haven't been on call, and you got in this weird time of like 2, almost 3 a.m. on a Sunday. You get this notification, whatever the system you're using, okay? And you have an issue with some code that you're unfamiliar with. All right? So what did it happen to anyone? I don't know if you can show hands. Maybe you can raise your hands in the Gather platform that I can see. All right, didn't happen. All right, it's going to happen. So even when the code works well, you haven't made any changes, things happen. You have dependencies, things change under your feet. There are some latent bugs. You upgraded hardware, and then the latent bug surface, and then you have this problem. You've never seen this code. What do? The common answer typically in a lot of places, let's call the person who knows this code, or maybe let's call the person who knows everything. All right? So let's go to this phenomena that I call the hero engineer. So now let's try again, a show of hands. Who here is a hero engineer in their team or in their company? Okay, so what is the hero engineer? The hero engineer is a type of engineer who can address almost any problem very quickly. The hero engineer knows a lot about a specific system. The hero engineer, if there is any issue, any outage, you call the hero engineer that can address it. If there is a bug, the hero engineer can easily address any bug because they know everything. They know all the details. The hero engineer can also evolve the system. If there is an important client feature, the hero engineer knows exactly what to change and what not to change. The hero engineer will know that, hey, if you change it here, you also need to change it there, unfortunately. It's all great short term, but this is definitely not good for your organization. And I'll explain why. Obviously, the pluses are obvious. There is any problem, the hero engineer can come and fix it, even respond to that outage at 3 a.m. You have a key person risk. Okay, what if the person goes on vacation? You don't want to bother them on vacation. They're going to tell you, yeah, you can call me, but you don't want to do it. What happens when they retire? In our company, it's not uncommon for people to stay for a long time and move around. Some of them stay for a long time in a certain position and they just enjoy it. But what happened when they eventually retired? Last week, I attended a retirement party of a person. It is not good also for the person. It is not fair. Always bother the same person for the same issue of hours escalation. Eventually, they're going to burn out. They're not good for their career. They're not growing. They're not evolving. They just keep doing the same thing again and again in the same system. It's also not good for other engineers. So imagine other engineers who may want to learn about the system, but they see that here engineer kind of entrenched in the system, so they're going to kind of stay away. They're going to look for their own niche. So it's not good for them. For them, if you put them on this system, it's going to be a whole new field that they're going to learn and grow and contribute to. Last but not least, is also not good for the system itself. The system, even though it may be stable, you may have a person responding to any issues, the system is not getting fresh ideas. And when you have a person who has been knowing and working on the same system for like many years, I can almost guarantee you, if you bring a new person, you get better and new ideas. I want to mention what I consider like the SME fallacy. SME stands for subject matter expert. A lot of time in companies and teams, we say we need an SME. We have an SME on this system. Typically, when we say SME, people think about knowledge. That person knows a lot about that system. They know what to change and where. But I think that's a fallacy. We need to look for SMEs who have more of a skill set in software engineering rather than a system-specific knowledge. For example, this person is an SME on Python. This person is an SME on C++. That person knows how to refactor any legacy code, et cetera, et cetera. So we should keep that in mind when we think about developing experts. We want expert to be in a particular skill rather than hoarding knowledge about a specific system. So what can be done? What can be done in order to kind of break this cycle? We need to appreciate the code that got us here. And when I say appreciate, it doesn't mean we look at a code and we say, this is the best thing, and that's how it should be. Because we know it's messy. We know that if we had to redo it again, we would do it differently. Appreciate means we need to understand why it looked the way it is. We need to understand that some errors, we have no idea why it looks the way it is, and we can question this. And we need to know what can be done and what is unlikely to get done. A lot of people tend to default to rewrite complex legacy code. That is typically not the right answer. It tends to be a popular answer because writing code is easier than reading code. I'm going to say it again. Writing code is easier than reading other people's code. Rewrite tends to be expensive. Okay? Rewrite tends to be time-consuming, and we found that very often a rewrite is not necessary. It is likely the wrong solution, and there are a lot of, unfortunately, good companies who actually failed because of a big investment in rewrite, complete overhaul. You pick the right term that you like to use. Okay. Any new code that you write is a future legacy code. So when you write new code, you have to really think like, what am I doing differently? Or what do I know that these people didn't know? Maybe the people who wrote the legacy code were not software engineers at all, or not good software engineers. It does happen in some companies, and I'm going to do it much better. Maybe all the bugs that were introduced 30 years ago and have been fixed through the past 30 years by running the code, I'm not going to introduce them again. Unlikely. Okay? In legacy code, even though it is messy, sometime you're going to find out a lot of the bugs have already been fixed. Very rarely it has all of a sudden a bug in terms of functionality. As long as all the code is being exercised and there is no new path all of a sudden because of a new use case, there are going to be very few bugs in the code. So it's doing its job. Otherwise, it wouldn't be stuck around. And it's very unlikely that when you're going to rewrite the code from scratch with a new language, doesn't matter how cool it is very unlikely that you're not going to introduce all the bugs that have been fixed. So What we can do, we found that we can invest and get a lot from restoration. So we found that you can get a lot of value with a little bit of investment in restoring the legacy code that actually we have. And what does restoration mean, right? It's a term we use in art when you take like some old picture or piece of art and you kind of clean it up, make it shinier a bit, make it presentable, put a protective glass if you've seen the Mona Lisa. So it's very similar. You improve documentation. Okay, most likely there is no documentation, so you're going to introduce some documentation. You add modern conveniences. For example, CI/CD. These are modern conveniences. When you restore legacy code, you do not need to use the tools of the time when the legacy code was introduced. You can use new tools, modern source control, CI/CD, automatic testing. All of these things can be done using modern technologies in order to restore your legacy code. Last but not least is standardization. By having things, especially if you have a large body of code, by standardizing it as much as you can, even simple thing as a formatting, you can make it easier to read the code. Remember, it's much harder to read code than to write it. So standardization of the documentation and of the code itself can help you, can help readers of the code having easier time maintain it.
So now I'm going to talk a little bit about what specifically we've done to invest in restoration and the specifics of the initiative that we're working on in that respect. So we've introduced this standard that we call TSAM. TSAM stands for Threshold for Stability and Maintenance. So basically, it's a list of criteria for our code to meet to make it more maintainable. And so there are 8 requirements for a piece of code to be considered TSAM. So the first is a standardized source control location. And this is because we want it to be trivial to locate the code if we have an emergency code change. If some latent bug is discovered and it's causing large issues, we don't want to waste a lot of time hunting for the source code. We want to spend that time actually fixing the issue. Second, removal of any duplicate copies from source control. So this is similar to the first point, but if you have multiple copies in like 2 different orgs, for example, in GitHub, those copies are going to diverge over time. And if you go to make a change and you make the change in the wrong version, you could potentially deploy a version of code that doesn't have some critical bug fix that was made previously because you picked the wrong version in source control. So we don't want to encounter any issues like that. 3 for us is moving to a CMake build. It's not really important what the build system is. The important thing here is that we pick a standard build system and migrate everything to build exactly the same way so that it's standard. So we happened to choose CMake, but it really is not important what that build system is. 4th, continuous integration of build and unit tests. So if a breaking change is made in one of our dependencies, we want to know immediately. We don't want to wait until we're doing some critical enhancement or critical bug fix to find out that because one of our libraries made a change, they broke our build and our code's no longer building. 5th, automated formatting applied. So consistent formatting makes code much easier to read. But engineers have more important things to spend their time on than making sure that their brackets are on the right line or making sure they're using tabs instead of spaces or things like that. So we don't want to waste engineers' mental energy. That should all happen automatically. Next, automated package creation. So we want to minimize any manual steps for publishing packages in order to decrease the potential of human error and increase our engineers' productivity. The last 2 we're going to talk a little bit more in depth about a little later on, but they are purpose level documentation. So we want to be able to easily identify what a piece of code does in general. First of all, in case an issue is found, you can easily identify the impact of that issue. And second of all, if an enhancement is required, it should be easy to identify what components need to be changed in order to make that enhancement. Finally, documented post-deployment validation process. So we call this a post-deployment check or a PDC. So we want to be able to ensure when we roll out a change that nothing has been broken, and testing environments aren't always perfect. So maybe something gets through testing, but then when you go to roll it out, it's not working correctly. We want to catch that before it makes it to production. So these last 2 points we've accomplished by introducing an additional standard that we call the ALDO standard. ALDO just stands for application level documentation. And what that standard is a pretty robust standard developed for application READMEs. It defines formatting rules, what sections are required, and specific terminology to use for PDC instructions. And the idea behind the ALDO standard, the driving force, is that we want a brand new engineer who's just come out of training to be able to read this document and understand at a high level in general what this piece of code does and how to work with it. We don't want engineers to have a lot of ramp up time just to understand the basics of what a piece of software does. So what does ALDO look like? First, we have the title. So this is the application name or the library name. Next is the TSAM badge. So today we're talking about TSAM level 1. There are also standards developed for higher levels of maintainability, TSAMs level 2 and 3, but we're not going to be talking about those today. But what this badge signifies is that this piece of code is at this TSAM level 1 standard. Next is the purpose. So the purpose is a one-liner just describing what the application is for, just at a glance. The mnemonic is what any abbreviations in the name stand for. At Bloomberg in particular, we really love acronyms, and a mishmash of letters don't always give you a whole lot of insight. But when you know what those letters stand for, that actually a lot of times gives you a lot of information just based on the name alone. And then a table of contents showing what else is coming in the README. Next up, we have our description. The description is really the meat of the README. The length can vary widely depending on how complex the component is, but it's usually the longest section of the README. And it should explain what the code does, what systems depend on it, what systems does it depend on, and at a high level, how does this component work? So the idea is we want to provide enough information to give insight into what the component is and what it does without getting too much into the details of the implementation, because implementation details can easily go stale if changes are made to the code. And so that kind of documentation is better suited to inline code comment documentation. The description section can contain any subsections that help organize the thoughts of it because it tends to be much bulkier. And it often contains diagrams such as flowcharts or sequence diagrams to help illustrate what the component does and how it works. After the description, we have build instructions. So the build instructions, like we said, part of the TSAM requirements is standardizing how things build. So this ideally should link back to generic build instructions that are the same for every component. But we still want to have that link in the README because we don't want an engineer to have to go digging for those instructions. It should be easily accessible right there from the code. We have deployment parameters. This just goes into instructions on what machines this software needs to get deployed to, what pace it should be, progress through stages, things like that. a testing section. So this describes what kinds of tests exist for this component, how to run them, any considerations with those tests, any details like that. Probably the second biggest section tends to be the post-deployment check section. The post-deployment checks are broken into goals. Each goal is a general overview of what the next set of instructions are trying to accomplish. Each goal is comprised of steps, and each step is a discrete, bite-sized, easy-to-follow instruction, such as run this command, or click this button, set this field to this value. There shouldn't be any room for confusion in a step. They use very specific language in order to make them easy to both understand, because there's no room for ambiguity of terminology, and it makes them easier to write. Engineers are by and large not writers, and we shouldn't be spending our mental energy deciding what words to use and what language to use. The steps may utilize what we call common operations, or COs. So COs are generic instructions that are used by multiple components. This links to a separate document rather than copy and pasting the same instructions if it's used in multiple places, which reduces the amount of typing required, and it also makes it easier to maintain. So if some step in a CO changes, you don't need to, Control F and find every place that instruction is used. You just need to go to the CO and update it there, and that'll update it for every component that uses it. And finally, the PDC may contain different instructions for different stages. So not every check is going to be safe to do on production, and that's okay. The idea is to document whatever checks we can safely do. So if you have a check that can only be run on pre-production, that's fine, document it. The final two sections we have are recovery. So this is how to normalize the system if we encounter an issue. So imagine you're rolling out a change and you're doing your PDC checks and it fails. What do we do now? So of course, the first step of the recovery is always going to be to back out the change. But in some cases, there may be additional steps required to normalize the system. For example, if the component is responsible for running a scheduled job and that job has already executed for the day, you may need to manually run that job again. And the idea of this is we don't want to have to spend time digging up this info when trying to recover from an issue quickly, because in those cases, every minute counts. And finally, references, just links to anything else that might be useful or interesting in trying to understand this component. So I'm going to hand it back to Haim now.
All right. Thank you. Thank you, Lainey. So you see all of that and you're wondering what you can do about it in your team, in your organization. You may be working for a very large company, for a small company. Each has its own challenges. We actually want to convince you that you can actually make something that will improve your life at work. So certain things you can do now. First, you can measure the problem. Divide your software into components. Whatever your components are, could be files, could be programs, libraries, databases, UI, and ask yourself, for what percentage of all these components you can say yes to the following? I know what it does. I know how to build it in case this is a compile language. I know how to deploy it and do it safely without digging for more information. So again, what it does, how to build, and how to deploy. Okay, and deploy is not only like, hey, what do I run to install it and go home? It's what do I run to install it and to actually see that it's doing what I expect it to do. And come up with this percentage. Show it to your peers, show it to your management, and try to assess the risk of having this percentage lower than 100. Right? Second thing you can do is try and quote unquote T-sum. We're going to have the deck. try and tease on one of your applications or one of the components and see what does it feel like. What does it do to the developer experience in the team? And get feedback. Our experience have been that for any software that reach that level, there is a dramatic improvement in quality of life at work for the engineers. They can focus on actually getting the job done, fixing a bug, adding a feature. They don't need to talk about like, who do I talk with or who do I need to call to figure out what is this thing. Okay, so try and do it, and pick a standard. It doesn't matter. Like you have in the deck all the qualification of what TISA means, and try to do it for one of your smallest applications. Last thing you can try and do is adopt a documentation standard, a robust one. Okay, create like a template, and try to follow the template. It doesn't matter the specifics of the template as long as it has the important sections that I mentioned earlier. What is this thing and what does it do? How do I build and deploy it? And you can add additional things, but this is the minimum. You know what it do, how to build, how to deploy. And use that standard and try to proliferate it in all your code base of your team and maybe eventually your company. We've been trying to do it it started in our upper organization, and we are iterating we're progressing very fast toward finishing all our team assets to be in that level. And I can tell you there is there is a big difference between not having it and having it. It's unbelievable how much little TLC can actually do. So we're gonna get to close this and leave some time for questions. But some of the takeaways that we think are most important from this talk. First, hopefully we're able to convince you that relying on a single person knowledge for anything, a single component, a single system, sometimes it's within the same company, it's a dangerous thing. If you want to have a sustainable long-term business, don't do it. Yeah. So legacy code doesn't need to be rewritten in order to be great. It just needs to have the ability to evolve and some basic documentation of what does it do. So people at least have some clue where to look, what to do, what are the boundaries, or as I like to say, the blast radius of touching this thing. A bit of an investment, as I said earlier, just a bit of an investment in TLC goes a very long way on making legacy code more pleasant to work with. And we've seen it happening in our team when we actually get work done. First question people ask, when we get work to be done, first question that people ask, is it TSAM or is it not? And we've seen like the difference in efforts and sizing when it comes to TSAM code versus not TSAM code. And it's much more, to be honest, it's much more fun to work with. You're going to be happier at work if you have code at that level. Another takeaway is standardization. So standardization is powerful because it develops what I call a muscle memory. Okay, if you have standards, yes, it's a bit tedious at the beginning to get used to writing in the standard, but let me tell you, it's going to go very quickly and you're going to get used to it. And on the reading side, the person who is reading it, it's much more flowing. They can read one application, then they're going to read the other application. They're going to have that muscle memory. They know where to look for what. Okay. The last takeaway is remember the SME fallacy. Subject matter expert. Skills are much, much better than information. Have an SME and have that SME based on skills. And most likely, you have right now SME which is holding, not by bad intention, just having a lot of information in their head. Put them to work and get them to stop disseminating the information on demand to other people and instead write that information. Maybe in that documentation standard that you're going to develop. So with that, we want to thank you again. I hope we have enough time for questions. here you have, while I want to pause and see if we can actually get questions from the crowd, but here you have on the screen, if you want to actually join us to this initiative on TSAM, you're going to scan the QR code to the left. And if you want to look at all the engineering open positions, you're going to scan the QR code to the right. And I think, Scott, do we have a medium by which to ask questions?
Yes, I've asked people to post their questions on the chat, and then I will relay them to you all. So one person has asked, what's an SME?
SME stands for subject matter expert.
What was that again?
It stands for subject matter expert. So someone who's the domain expert in a particular either system, or that we're discouraging from that and encouraging SMEs for specific technologies instead.
Okay. Awesome. So someone has asked where they can find the templates for TSAM and Aldo.
This is an excellent question. Right now, they are not available for public usage. I'm going to circle back on that. And I know that there are people who want to make that more internal standard. So maybe one takeaway for Lainey and me is to go back to our company and see if there is an interest and ability to actually make it an open standard, at least. Because the Aldo itself, there's nothing there that is unique to us. It's more about a meta standard. It's about writing standard documentation. So that's a good point. You're gonna look into it. That's a good idea. But you can have the slides, and you can have, like, from what we capture here, get some idea. The standard is more about, Lainey, correct me if I'm wrong, the standard is really pedantic about, like, you should be using these words. And I give credit, it was written by a former colleague who's really sitting in a lot of standard committees. If he's here, he's going to show up himself. If he's not, it's fine. But you don't need all of these things to start with. You can start with something as simple as, hey, what do I need in the documentation? Like, and as Lainey showed, why is it called like that? What does FOO stands for? FOO SVC. Okay, it's the FOO service, but what is FOO? Right? I once dealt with a code that the name of the app was triple O, and we couldn't figure out what it is until we discovered is some acronym, object outage or something like that. So start with a name, have the description, what it does. You don't need to know the entire system. We found that it is sufficient to just kind of draw the boundaries. So here's a program that runs daily. What are the inputs? Great. What is the output? A file. Okay. You may not know how the file is being used. That's okay. But at least you have the boundaries. And as you do it to all the components, eventually you'll be able to construct a puzzle. Okay. So what does it do? How do I build it, or how do I even test it if it exists? And how do I put it in production and make sure it didn't break something important? Lainey,
it's less important that you use our standard and more important that you use a standard that has these components to it. So I don't think it's necessarily important for you to have the details of our standard. You can take the big chunks and develop that into your own standard, for sure.
Gotcha. So there's another question here. You document how to normalize system. Do you practice it? The person said they'd love to hear stories.
Yeah. Lainey, do you want to talk about the last step in a TSAM of a component?
Yeah. So the final step when we're done TSAMing is that we roll out the system or the component. So and we actually started having the person who does the rollout different from the person who did the TSAMing. And that allows them to almost validate the PDC instructions because they have to follow them without the previous knowledge of being the person who came up with them and wrote them. And that identifies really well any like ambiguity or any missing steps, any gaps there that the person writing it may have just assumed because they just spent a lot of time digging into this component and figuring it out. In terms of the, you were specifically asking, I think, about the recovery section. Usually that's tested in a test environment, but not necessarily tested in production, because it's not always safe to do it in production unless you are recovering from an issue.
And we did have our own fair. You can imagine, as we took legacy software and renovated it, we did have tiny bit of opportunities to actually roll back and return to normal, because things didn't, when you take when you improve a system, not everything works as expected. So we got to practice it, but it does involve a risk. And the other thing about return to normal, they're typically recovery is typically pretty standard. So if you have something, let's say a web service, there is a standard mechanism to restart it. If there is a job that runs on a schedule, there is a standard mechanism to rerun it. I hope, Michael Wolf, this is answering your questions. I do want to make a comment. There is a comment there we'd like about GPT. As a policy, we're not using GPT. There's a lot of problems that exist right now with GPT. If you read about it, like who owns the output of ChatGPT? So at the moment, it's not being used. And if you look on LinkedIn and follow Bloomberg, you'll see that we're actually developing our own unique large language model. So hopefully we will have an in-house solution for that.
Awesome. Another question that has been asked is, have you experienced any resistance to adopting TCM? And kind of more specifically, the person who asked can imagine people balking at the idea of going back and documenting a system because it's not fun.
So people tend to be hesitant at first when it comes to the actual doing of it, but it's a much easier case to make when you have a couple of components that you've already done and you say, hey, look at this, look at how much easier this is to work with, look at how much better a developer experience this is, and how much faster it is to do other work that we need to do on this component. It's hard to argue when you have that example, and you can really demonstrate how much of an improvement it is into the quality of life of developers.
I believe the question about resistance was maybe not about disagreeing that is a good thing, but kind of not want to be the one doing that. And I can comment about that. So yeah, I did see how almost everybody want to work on a code that is TSAM, but very few people are actually interested. And in the way we address this, we just got for this specific project, we got people who are good at this and are interested. We specifically looked into people who to get involved, people who are good in digging stuff, people who like reverse engineering, people who look at everything as a puzzle. So I think that's the takeaway, at least for me. Lainey, what do you think?
Yeah, definitely getting the right people who are actually interested in it.
Yeah, but we didn't see resistance. Everybody saying, no, we shouldn't have this. It's a waste of time. Everybody thought, oh, that's a great idea. I want to do it too. Show me how.
Awesome. And then I think perhaps the last question, I think it's probably the last one we'll have time for, is after an incident, do you do a retrospective on how well the rollback documentation worked, kind of in the context of actually applying that to a real world issue?
Oh, definitely. Whenever we have an issue, we do a retro. And if one of the issues was like a hole in the documentation, we'll absolutely go and update that based on the outcome of that particular outage. I think the important thing to remember is that documentation is ever evolving, but it's a lot easier and people are a lot more willing to update documentation when that documentation already exists. It's a much heavier lift to write new documentation from scratch than it is to go in and tweak some existing documentation because, this particular line has a typo in it, or the command the path to this has changed, and so we need to fix it now. People are a lot more willing to do that than write brand new documentation.
Yeah, the framework and guardrails are already there, and it's so easy to add, and it's actually embarrassing not to add. The other thing about nobody asked about like automation. we write a lot of documentation, and when we have an opportunity to automate based on how often we need to deploy a piece of software, it's easier to automate because now we have a spec of what actually we need to test. So that's another benefit of that documentation.
Nice. And then I guess we do have just a few more minutes, so I'll toss in a question I have. Do you all have any practices that help you keep that documentation from drifting away from the implementation? You might have touched on this a little bit already, but that's something that I'm always worried about, because there have been so many components and so many systems that I've worked on where I walked in and I trusted the documentation to be accurate, only to learn later that it wasn't.
So there's a couple things I'll say to that. For the first one is that the storing the documentation in a README in the code base makes it a lot less likely for drift to happen, because it's right there. When someone clones the repo, they have the README. So if they're making some change, they're more likely to update the documentation as well because they see it right there. The second thing I'll say, and I did touch on this a little bit in the talk, is we try not to go too much into the implementation details in the README for this exact reason. So the description should be more about what it does at a high level, and how it interfaces with its dependents and its dependencies, and in general what it does. Then it should be about specific implementation details, just because of exactly that reason.
Okay.
And that is definitely a balancing act. Part of my job is to review these as they're being written, and a lot of times I'll go back and say, this is really good information, but I don't want to include it in this doc because it's likely to become stale.
Yeah. I would add also, I think, Lainey, it's worth mentioning, we try to avoid as much as possible any diagrams that are hard to modify. We try to generate them on the fly from the text. Some of the README has in it embedded plant.uml to generate simple diagrams, because we don't want to end up with something that looks very beautiful, but then in a few years it's stale. But the key ingredients I found is just have the README, the markdown in the same repo, ideally in the same directory with the components. It's so easy and it's obvious. I haven't encountered any case yet of somebody who actually forgot to do it.
Awesome. Well, thank you both very much for kind of kicking things off with our keynote. It's been great having you here, and hopefully, if people have further questions, they'll be able to bump into you later today if you're able to stick around. And everyone else, their next talk on the main stage, or I guess the next thing that we've got going on the calendar, is the open space, which will be in the other room. So if you're in this room and you want to participate in the open space pitch session, you need to go to the other room, the main lobby. And that will kick off in about 10 minutes. So thanks a bunch, y'all, and chat with everybody else later.
Thanks so much. Bye.
Thank you.